Good evening, everyone, and thanks for coming. So today, in this session, we are mostly going to demonstrate how you can implement your own Kubernetes scheduler and show a proof of concept network-aware scheduler, which we call it as SchedNet. My name is Akash Gangil, and I'm a software engineer in Ohana. And
if the mic works, my name is Salvatore, and I am a software engineer instead at VMware.
Yeah. So during the next 30 minutes, this is how we have structured the talk. So first, we are going to talk about the default scheduler in Kubernetes. We are going to show how it works and like what are its drawbacks and how you can improve upon it. Thereafter, we would discuss our network-aware scheduler, which we call SchedNet. And we talk a little bit about OVN, since that's the component that we use for networking, to provide networking to the Kubernetes containers. Then we'll talk about the setup topology, followed by a demo, and then we'll discuss the results. So let's start off. So I guess most of you would be already familiar with the scheduler component in Kubernetes. So scheduler is a component which makes decisions on where pods in your Kubernetes cluster should be placed. So by default, like Kubernetes provides a default scheduler, and to actually see how it works, let's just take a scenario example. So let's say we have 5 container hosts or minions in our cluster. And as soon as a user creates a pod spec in the Kubernetes cluster, the scheduler keeps on checking with the API server if there is a pod that's unscheduled. And by that, what it means is like if there is a pod spec resource in the API server for which the node name is not yet specified, at that point of time, the scheduler kicks in and it works on finding a container host for that particular pod. So let's assume like the user scheduled a cluster and the scheduler kicked in, and like there were 5 nodes in our cluster. So the process is like can be considered as a 2-step process. So in the first process, in the first step, what the scheduler does, it applies certain predicate functions to all the nodes in the cluster. So, and these predicate functions are basically used as a filtering mechanism as to whether that node is fit to run that container or not. So we run that list of predicate functions on all the nodes in the cluster, and thereafter we get a filtered list of nodes. So like in this case, for example, like we applied the predicate functions on nodes N1 to N5, and the scheduler found that only N2 and N4 satisfied whatever the pod criteria was. So this is the first step in the scheduling process, and the next step is, as can be guessed, is deciding which among these nodes is a better fit. So for that, the scheduler applies certain priority functions to these given set of nodes. And by priority functions, it's pretty much a way of quantitatively saying that which node is better suited for that particular container. So there are a bunch of predicate functions, and what each of the bunch of priority functions, and what each of them returns is an integer value. And ultimately, for each of the nodes, we take a weighted value by running it over all the priority functions, and then we just sort the weighted score of all the nodes, and we take the topmost node. So in this case, the scheduler applied those priority functions on N2 and N4, and it found that N4 is more suitable for scheduling that particular container. So I think it's pretty simple and straightforward what it's trying to do. To get a little more like idea of what the default, what the predicate and priority functions look like, let's look at like some of the sample predicate functions that Kubernetes applies by default when it's trying to schedule pods. So like the first one is the host port check. So in Kubernetes, you can specify a host port for a container if you want. So what that actually means that the container port has to be mapped on the host port. So that port needs to be available on the node. So this check makes sure that if, say, you have specified host port 80 or 90 in your pod spec, that port is available in the node. And if it's not, then that node is not suitable for scheduling the pod. The other one is pod fed resources. So by default, in terms of resource measurements, like the scheduler is only taking into account the CPU and memory usage of each of the nodes in the cluster. And this is reported by the kubelet back to the API server. And recently, there's some support added for GPU as well. But like that's all that they're talking about, like when we look into resource usage on each of the nodes. And third, similar one could be like seeing if a node, if a pod spec has specified a node selector, and then the user means that that pod should only run on the nodes which have that particular selector. And that could be because they have some special requirements for the pod to run. So the match node selector predicate tells whether this node is suitable for scheduling or not. So I guess, so these are just 3 of them. So I guess there are a total of 7 or 8 predicate functions which are specified by default in the scheduler. Next, moving on to like what the priority functions look like. So these are the ones which are applied in the second stage of the scheduling process. So like the first one could be the selector spread. The name, it might be confusing for some. So what it essentially means is when we are trying to deploy a deployment or replication controller or service in our cluster, the scheduler wants to make sure that all the pods or containers backing that particular abstraction, like the service or the deployment, are not concentrated to a single node in your cluster. So this essentially checks to spread the pod among all the nodes in your cluster. So if a node for that particular deployment is already on a node, that node would be given a low priority or low score when the other pods for that service are to be scheduled. Similarly, we have image locality. This is pretty self-understandable. Like if a node already has the container image, then obviously it's given a higher priority. Least requested nodes, it's again like you want to schedule resources, pods on nodes which are underutilized to have a more uniform distribution. And similarly, node labels. So node labels differs from node selectors in the way that selector is more like, it's a more harder condition versus a node label. A node label is just like a compatibility check that if this label is present, then good enough, else like give it a low priority. So in a nutshell, what we are actually looking at, what the current scheduler does, it takes a list of nodes, applies some set of predicate functions, which filters a list of nodes, and then we just sort the remaining nodes based on some priority. And ultimately, we get a node on which the pod is scheduled on. Now, obviously, like there are like pretty obvious drawbacks which one can think about. Like one is the scheduler right now is using these set of predicates or priorities for all the pods, irrespective of what application or service they are running. So whether it's like a network intensive app, like a video application, or it's like a machine learning or a ray tracing app, like which are more compute intensive. So the scheduler is not really taking into account the type of applications it's trying to schedule. So that's like one of the things that could be improved. The other thing is like the scheduler is not getting any information from your like the underlying topology. Ultimately, like the clusters on which we deploy our systems they are heterogeneous. Not all nodes are similar. Like some might have better hardware than the others. So that could be that either the users can specify node selectors, but that's something that's not taken into account by the scheduler itself. And the third one is, as we talked about the weights in the second step of prioritizing the nodes. Right now, the default implementation, the way it is right now, it takes all the priority functions equally. Like everything is weighted as 1. So like those are some of the things that like the default scheduler is not really handling and can be improved on. But the good part about it is like Kubernetes scheduler provides a lot of hooks where you can plug your own scheduler or like make changes to the custom scheduler. So, I mean, natural inclination like for anyone is like if they are running a cluster, then how they can do a better job. So first is like when we are prioritizing the nodes, we think of prioritization as more in a quality of service sense, and like quality of service can be pretty broadly classified. Like you could have networking, storage, and all the things that might impact the performance of your application. So if we take that into account while prioritizing nodes, that could be a good metric. A similar one could be like which we also tackle in our proof of concept scheduler is we try to balance the bandwidth usage of all the nodes in your cluster. So like if there are some applications which are very network intensive and some others are not, then those applications should be uniformly distributed in your cluster. So in this case, the applications which are running in the pods. And then you can also like try to play around with the weights that the default scheduler already provides us. So now to just show like how we can improve it, we worked on the scheduler called ShedNet, and I guess Salvatore is gonna talk about some of the details.
Well, actually, this mic works, so you can keep your position there. So we start with OVN, which is an acronym which stands for Open Virtual Network, which is the network backends that are using in this POC that are demonstrating today here. So anyone is already familiar with this particular network backend? Well, apart from you guys, I know you. Well, anyone that has never heard of this, like this is the first time in my life that I heard of this? Okay, so I can't assume that you heard of it and that you discounted it as something terrible, which I would understand, but I would try and ask you to reconsider your opinion because it's actually quite good. I mean, I am partial, but I think it's actually quite good. It is entirely open source. It is developed by the Open vSwitch community, and if you want to look at the list of contributors, of course there is VMware, but there is also a lot of contributors from Red Hat, HP, Intel, and a lot of companies that I'm probably forgetting about. And in terms of more substantial things, it creates management of it allows to create and manage virtual network topologies, layer 2, layer 3 topologies, and it also provides security through stateful ACLs, and it has both a layer 4, well, it doesn't have a layer 7 load balancer, Akash. It has a layer 4 load balancing services, and it can be easily integrated with ingress controllers such as Nginx on Traffic for providing the ingress feature. And also, it supports most Kubernetes features, and you can try out the Kubernetes integration for OVN at the address that's on that link. Trying out the integration is very easy, even if unfortunately we are not yet able to provide a kubeadm add-on, but at least it should not take more than an hour, maybe half an hour to set up a simple cluster with OVN integration. Anyway, OVN is not really the focus of our talk today, so let's look at our experimental testbed. So in this testbed, in the picture that you see there, it would be nice to have one of those pointy things. Otherwise, I have to dance around the screen like this and go on this screen. We have our topology, which is made of 3 kinds of components. In green, you have the OVN components. In blue, there are Kubernetes components. And the pink components are the sched.net elements that Akash will talk about briefly. So let's start with the OVN bits. On every node, where containers are running, we got a controller component. The controller implements the control plane and manages the Open vSwitch data plane instances locally. So it only holds state for managing virtual network interfaces on the local node. So behind this controller, there is, of course, an Open vSwitch instance. And on that Open vSwitch instance, we configure the node local interface. And then these controllers interact with that OVN NorthD daemon that you can see here, which is a sort of a northbound driver. It exposes, indeed, a northbound API for management planes like OpenStack, or in our case, Kubernetes. And that component, the OVN KTS watcher, is what makes the integration between the Kubernetes API server and OVN. Using OVN, we build this logical topology, which is made of one logical switch per node, which are interconnected by a logical router. Of course, when we say logical routers, this is just an abstract concept. There's not really routing occurring. It's a distributed router. So we never, if you have two containers on the same node, you never go through this thing. So it's all distributed. And for implementing the Kubernetes service abstraction, it doesn't leverage the kube proxy component, but instead it leverages OVN layer 4 load balancing capability to implement east-west distributed load balancer, and therefore two load balancer instances, one for TCP services and one for UDP services, are associated to each logical switch. So of course, this is a very simple logical topology, but it enables us to fulfill all the Kubernetes use cases, at least in this phase where we don't have multi-tenancy and multiple network support. When this will be adopted by the Kubernetes SIGNet and incorporated into Kubernetes, of course, this topology will change a little bit. So, and I think that this is all for the OVN side. We described the components and the topological topology. As you can see, the Kubernetes side, we have the usual components, the API server, the controller manager. As we said, we don't have the kube proxy on every node. And the kubelet is running the OVN CNI plugin, which, unlike other CNI plugins, is a very simple component that just configures the local network interfaces and plugs it into the OVS bridge instance. So I guess that is all in terms of the description of the components that we are running in our service. Of course, the most juicy thing is still missing, which are the net health agent and the sched.net component, for which Akash will give you a description.
Okay.
Yeah. Wait, where are you going?
Okay. This is the slide 2.
Yeah, I know that this is. I thought you wanted to do that. I'll do that.
Okay.
So basically, we have on every host, on every minion. Still using term minion. I don't know if it's friendly to use term minion. Mm-hmm. On every node, anyway, we have one agent that collects network health status, which Akash will see with Akash exactly later what this net health status is, but it's suffice to say that it is an estimate of the throughput currently being used on every node. And periodically, this net agent sends network state data to the Kubernetes master where sched.net is running. And now, sched.net is not really a replacement for the Kubernetes scheduler. It is more correct to say, correct me if I'm wrong, an enhancement of the Kubernetes scheduler. So it is still the same Kubernetes scheduler, to which we added something for making it network aware. So I think this concludes the discussion of the testbed, and we can go ahead and see.
Sure. So just to lay more details about the network agent, it's actually pretty simple, like something that we want to show quickly that, so the network health agent runs on all the minions in your cluster. And what it's essentially doing is it's capturing the node's network throughput and annotating that information onto the API server. Now, in this particular instance, that this information is network throughput that's collected by fstat, but you could have your own agents which could provide a little different information or something more optimal to your particular use case. And it annotates the API server via the patch endpoint, and with the annotation with the key value score, and key being the network health. So I think it's pretty simple, and one doesn't need to understand. So how it actually like works. So in each of the minions, the network health agent is collecting this network health score and updating the node annotation every 1 second to the API server. So now whenever a pod is scheduled and the scheduler notices the need for it, so it gets to know that the scheduling function kicks in, and what it actually does, it reads the network score for all the nodes in the cluster, and based on that particular information, it makes the decision on which node should the pod get scheduled on. So as can be seen by 3. So let's just dive into the demo now. So in the demo, we have a 3-node cluster. So we have the Kubernetes master, the minion 1, and the minion 2. We are using the local up cluster script to set up our Kubernetes cluster, but it's not something that's like a design. Like it's just based on preference. Like you can use whatever you want. And secondly, the master is also running the OVN watcher that we just discussed during the OVN slides. And the minions are running the network health agent, as you already saw here. So it's posting this patch to the API server, and it's also running the kubelet as well. So that's what characterizes it as a minion. So in the demo, what I'm gonna do is what we want to show in this demo, that you can also modify the scheduler such that the network load is uniform across various nodes in your cluster. So we would schedule, say, 4 pods over here. So and those pods would be making pings of different packet sizes. So one of the pods, which is the Nginx 5 pod, it's pinging packet sizes of, say, 55 KB to a destination. And this IP address is actually an interface on the master node, which is set up during the OVN topology. And similarly, we have other nodes, other pods in our setup, and they are pinging packets of less sizes. So what we want to show is, so these are the other set of pods which are actually not that network intensive. So we have Nginx 2, then Nginx 3, and similarly 4. So Nginx 3 is pinging packets of sizes 3 KB, and Nginx 4 is pinging packets of sizes 30 KB. So now if we look at it, since we have the agents already running on the minions, so if we check the annotations, the node annotations, they already have scored. So I think okay. I'll just reduce this. So like the node 1 has a network health score of, say, 0.74, and the node 2 has network health score of 1.72. And the reason it's not 0 is because OVN, to make sure that tunnels are up, it has some gossip traffic which actually makes sure that things are working properly. So that's why right now you're seeing that it's not 0, although there's no pods in our cluster. So now we would go ahead and deploy the pods in this setup. So one thing that I think most of you, since you would have played with Kubernetes, like by default Kubernetes would just schedule the pods like 2 on each of the nodes. But in this case, hopefully like the pod with the high network traffic is scheduled on one node, and the subsequent pods are scheduled on another node to make the load more uniform. So let's just go ahead with that. So The network connection is a little slow. So we just created the pod which had ping packets of large size. So if we see that we scheduled it on minion 1. Now if we schedule the other nodes as well. So like this got scheduled on minion 2, and so let's just go ahead and schedule other pods as well. And so as you can see, like the rest of the pods were scheduled on different node and not on the node where Nginx 5 was scheduled. And the reason being is as these pods were getting scheduled, the network agents on the minions were reporting the metric or the network health score as these pods were getting scheduled. And because of that, the scheduler took those health scores into its scheduling decision, and it placed the remaining pods on other nodes. So if we just see that the network health scores now, so it tried to balance, so 126 health score is given to the node on which Nginx 5 was scheduled, and the other one is 66.09. The way this computation is done is just a 1 by logarithmic throughput, and it's scaled by a factor of 100, which you could also consider as a weight of that priority function. So I think this is pretty much what we wanted to show, that you can implement. You can customize the default scheduler such that to able to better meet your needs, and which could range beyond the general CPU and memory resources which the scheduler considers. So what we essentially saw that we had 4 pod specs which we wanted to schedule. In case of default scheduler, they are scheduled more evenly, like 2 pods on each node, in which case the network load is not really distributed. While in case your scheduler takes the network load into consideration, then it's more uniform. So now there could be multiple approaches in which you can do this. I guess there was another talk on data-aware scheduling where they implemented their own scheduler. So you can also go ahead with implementing your own scheduler completely outside. So and what that would entail is you're not touching default scheduler in any way. You deploy your own scheduler, and whenever you're deploying a pod, in the pod spec you can specify the scheduler name. So that's another way in which you can specify a custom scheduler, or you can use the extender interface. So Kubernetes scheduler by default provides this another pluggable mechanism called extender interface, and under this, it allows you to define REST endpoints where you can define your predicate and priority functions. But I guess the downside of this is performance in some of the cases, like the scheduling time is much greater than what you would expect. So why would you actually even care about all this stuff? So like you would want to schedule your pods based on more data and more context in your topology. So I'm not sure like how many people use like software-defined infrastructure, but you can use in terms of network and in terms of storage. Your infrastructure could entirely be in software, and what that allows you is the programmable nature of that infrastructure allows you to leverage that information into your scheduling of the nodes. Then again, you have a heterogeneous set of applications, as I mentioned earlier. Like not all applications are equal, and there's no one-size-fits-all solution for everything. And like it's pretty cool. Like Kubernetes allows you with so much ease that you can experiment with what you want to do. So this also also aimed at highlighting that. Yeah, I guess that's mostly it. And if there are any questions, I'm happy to take them. Yeah. Thank you.